We will continue with the review of basic concepts in multivariable calculus. Okay, so let me share this document with you. Are you able to view it?
Yes, sir.
Okay, so if you are facing any problem, please let me know. Okay, so I'm going to spend some time discussing the basic concepts of partial derivatives and differential. Okay, so again, the students who are doing pure mathematics or whatever, applied mathematics, yeah, please bear with me. I'm sure that you are all quite familiar with these concepts. Okay, but just for the completeness sake and for by keeping in mind the statistic students, I would want to review these basic concepts. Okay. So first, let us define directional and partial derivatives of functions of several variables. Okay. See, again, I'm not saying that the statistics ASI students are not familiar with these concepts, but some of them might have forgotten this because we don't uh, encounter them that often. Okay, so for example, we're going to see the definition of a function from Rn to R being a differentiable. So we don't encounter such concept that often. Okay, so that's why just my idea is to refresh their memory. Okay. Uh, so first, okay, let's begin with definition 3.1. So let phi be a unit vector and x be a point in Rn. Then the directional derivative of f at x, where x is a point in Rn in the direction of phi, which is a unit vector, is defined by this. So essentially, you look at the quotient f of x t plus phi minus f of x divided by t, and you let t approach 0. Okay, and whenever the limit exists, this is referred to as the directional derivative of f with respect to the direction phi, and this is being evaluated at x. Okay, so this is what the definition is, and well, this can be thought of as the ordinary derivative of this function. Okay, so you let ht be equal to f of x t plus phi and look upon this as a function of t. Then this is a function of t, so the ordinary derivative of this with respect to t evaluated at t equal to 0, provided the ordinary derivative, the limit exists, then this is same thing as this. Okay. So just let me illustrate this concept with the help of example. So let phi be given by phi1, phi2, phi3. It's in 3 dimension, and let f of x, y, z be given by this function. Okay. So h of t, which we defined as f of x plus t times phi, will turn out to be 3 times x plus t times phi1, the first element of phi, then y plus t times phi2, second element of phi, and so on. So x, y, z. So this function is being evaluated at x1 plus t phi1, comma, sorry, not x1, x plus t phi1, y plus t phi2, and z plus t phi3. And so you replace x, y, z by those respective elements, and this is what one obtains. Okay, this is h of t, and the derivative of this with respect to t and then evaluating this at t equal to 0 gives us the partial derivative of f with respect to this direction phi evaluated at x. So this is the derivative. This is the directional derivative of f in the direction of phi evaluated at x, and is given by this. Okay. And the directional derivative that we are most interested in are those in the directions of the unit vectors. So let E1, E1, E2, En represent the n unit vectors where Ei is a unit vector where the ith element is equal to 1 and rest of the elements are 0. Okay, that is how Ei is defined. And these are the unit vectors, or these are the directions in which we are interested in. Okay. And since x and x plus TEI differ only in the ith coordinate, so the partial derivative of f in the direction of the vector EI evaluated at x is called the partial derivative of f with respect to xi, the ith element of x. And it is also denoted by delta f by delta xi evaluated at x, or it is denoted by f of subscript xi evaluated at x, and thus by definition actually this is equal to this. Okay, so f is being evaluated x1 plus t comma x2 dot dot xn minus f of x1 x2 xn divided by t, and you let t go to 0. Okay, and this is so essentially x2 x1 x2 x3 xn are being held fixed, and then you are trying to differentiate with respect to x1. This is what you get. All right. Similarly, the partial derivative of f with respect to the ith coordinate of the vector x is defined as this: f of x1 comma dot x2 dot 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 xi minus 1. Ith element is xi plus t comma xi plus 1 dot 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 xn minus f of x1 dot dot xi minus 1 xi plus 1 dot dot xn divided by t, and let again this limit is taken as t approaches 0, and this expression is valid for I starting from 2 to n minus 1, and the partial derivative of f with respect to xn, so f x1 x2 xn minus 1 xn plus t minus f of x1 x2 xn minus 1 xn divided by t as t approaches 0, and of course this provided all these limits exist. Okay, so if you write x is x equal to xy, then we denote the partial derivatives accordingly. And thus the partial derivative of f of xy function with respect to x by holding y fixed is nothing but the limit of f of x plus h y minus f of xy divided by h, the quotient, the limit of this quotient as h tends to 0. Okay, so again I think that's the standard definitions. Of course the limits have to exist. Okay, so it can be seen from these definitions that to compute the derivative of f with respect to the ith element of the vector x, we simply differentiate f with respect to xi according to the rules of our ordinary differentiation by treating the other variables as constants. Okay, so again, let's quickly go through this. So taking phi to be equal to E1, that is setting phi1 equal to 1, this is typo, and phi2 and phi3 equal to 0. Okay, in 1, this is what we obtain. So the partial derivative of f with respect to x by holding y and z fixed. Again, I think maybe there is typo here. If I take the partial derivative with respect to x, I'm left with 3yz plus 4x. So this x is not supposed to be there. That's a typo. I shall remove it, and which is the result obtained by regarding y and z as constants. Similarly, partial derivative of f with respect to y is 3xz and this and so on. Okay. Now next theorem follows from the rule just given for calculating partial derivatives. So again, so if this is the partial derivative of f with respect to the ith component of x, and this is the partial derivative of g with respect to the ith component of x, and if these partial derivatives exist, then the partial derivative of f plus g, that partial derivative exists and is given by this. Again, these are routine results. No point in spending time on this. Okay, so I'm going to skip them. I just Again, for completeness sake, I just mentioned them here. Okay. All right. Now, if the partial derivative of f at the ith component of x evaluated at x exists at every point of a set D, then it defines a function fxi on D. It defines a function fxi on D, and if this function has a partial derivative with respect to xa, the z coordinate of vector x on a subset of D, then we denote it by this. Okay, so this is again to be looked upon as a function whose domain is D, and then the partial derivative of this with respect to xa is this, and this is equal to f of xi, and this is denoted by f of xi xa. Similarly, further, this can be looked upon as a function on D, and then you take the partial derivative of this with respect to k, and then you can go on taking the partial derivative with respect to the other kth coordinate of the vector x. The function obtained by differentiating f successively with respect to xi1, xi2, xir is denoted by this, and it is said to be an rth order partial derivative of f. Okay, so again the same thing. I mean, I'm not, this is the function partial with respect to x, partial derivative with respect to y, then the partial derivative of this with respect to x, partial derivative of then this with respect to x is given by this, partial derivative of this with respect to y is given by this, partial derivative of this with respect to x is given by this, and partial derivative of y with respect to y is given by this. And if you go for the third order derivative, partial derivative, then these are some of the examples. So, take the partial derivative of, let's say, take the partial derivative of this with respect to x will lead you to this, and so on. Okay, so these are all elementary stuff. Now let's compute f of x 00, fxy 00, fyx 00, and this the function fxy is given by this. Okay, so again the ordinary rules for differentiation applied separately to x and y. These rules yield the partial derivative of this with respect to x is given by this. Okay, that can be easily verified. This is simple exercise, and this expression is valid as long as x and y, if this coordinate is not equal to 0, 0 coordinate. Okay, similarly the partial derivative of this with respect to y, again this is whenever xy is different from 0, 0, it has this formula. And these formulas do not apply when the xy is equal to 0, 0. So we find f of x 0, 0 and phi y 0 from the definitions, from their definitions as difference quotient. Okay, so fx 0, 0. So let us look at this. So this is by definition fx0 minus f0, 0, 0 x. Again, as x tends to 0, this can be easily shown to be 0. This can also be easily observed to be 0. No issues. Now by setting y equal to 1 and 3 and 4, okay, I did not, yeah, by setting y equal to 0 and 3 and 4, we get f of x 0 is equal to 0. So if you put y equal to 0 here, it is clear that fx 0, sorry, fx0 is equal to 0, fy0 is equal to sin x, x equal to 0, and so again fxx0 is fxx0 minus fx0 by basic definition. You get this to be 0, you get this to be equal to 1. Now setting x equal to 0 in 3 and 4 in these expressions here, the partial derivatives of x and y whenever xy is not equal to 0, 0. If you set y equal to 0, rather setting x equal to 0, this is what one obtains, and then the partial derivative of second order partial derivative will yield you minus 1 and 0. Okay, so again again nothing new is being told to you. So this example shows that fxy x0 at x0 is not said. So for example, fxy 0, 0 is minus 1, whereas if fyx 0, 0 is 1. So if yx00 turned out to be equal to 1, if xy00 turned out to be equal to -1, so order in which the derivatives are taken, that order matters. Okay. But this theorem provides us a sufficient condition for which the order in which the partial derivatives are taken should not matter. So the theorem, the statement of the theorem reads as follows. It says, suppose f, fx, fy and fxy exist in a neighborhood n of this point x0, y0, and if fxy is continuous at x0, y0, then fyx, x0, y0 exists and it equals fxy, x0, y0. Okay. So again, just in case some of you have forgotten this, I'm helping you recollect this result or help you recall this result. So suppose this again, so these partial derivatives, first order, second order partial derivatives in the function itself must exist in a neighborhood n of this point at, point at which we are interested in comparing the second order partial derivatives, and the function fxy has to be continuous at this point. Then the second order partial derivative fyx at x0, y0, this exists and these two are equal. Okay. Okay. Now next theorem says that, again, this is just a generalization of what we saw here in this theorem. So suppose f and all its partial derivatives of order r less than equal to r exist in the neighborhood of x0 in Rn and are continuous at x0. So these partial derivatives are continuous at x0. Then the partial derivative, this rth order partial derivative of f evaluated at x0 is the same thing as rth order partial derivative of f evaluated at x0 if each of the variables xk appears the same number of times in these two sets, and if this number is rk, we denote this common value of the above two sides by this. Okay, so again, let's not get bogged down by the notation. Okay. So I think again, so we are just, I'm illustrating this with the help of examples. And this theorem says that, for example, that if f satisfies its hypothesis with k equal to 4 at a point x0 in Rn, then the fourth order partial derivative, all these fourth order partial derivatives evaluated at x0 of the function f, they all coincide. Okay, and their common value is given by this. So the order in which the derivatives are taken is unimportant as long as this hypothesis is met. Okay, that's what this theorem says. All right, I think fine. Okay, now I think, okay, this is my probably, again, I must admit to you that I myself had forgotten all this definition. For example, the definition that I'm going to present. Because we, here we're going to talk about the a function f, let's say from Rn to Rn being differentiable, being differentiable. Okay, that's what we are talking about here. So we know what is meant by a univariate function or a function of one variable being differentiable. Everyone knows that. Okay, but we are considering function f from Rn to R, and we're trying to ask ourselves as to what does it mean to say that the function is differentiable here. Okay. So a function of several variables may have first order partial derivatives at a point, but it may fail to be continuous there. So for example, let me illustrate this concept. So let's consider fxy to be xy over x square plus y square, where xy is not equal to 0, 0, and whenever this point is equal to 0, 0, we set this equal to 0. Okay. Now fx 0, 0 and fy 0, 0. So you take the partial derivative and evaluate them at 0, 0. Then they can be shown to be equal to 0, but the function is not continuous at 0, 0, and that is obvious from here. Okay, the function is not continuous at 0, 0. Okay, that is pretty obvious. Okay, I think we have seen this example before. If you let x be equal to y, if you let x be equal to y, then and take the limit. So the limit as x tends to 0 will be equal to half. If you let y be equal to minus x, the limit will be equal to minus half, etc. So the limit itself doesn't exist. So there is no question of it being continuous. Okay, but the partial derivatives at x and y with respect to x and y, partial derivatives of f with respect to x and y evaluated 0, 0. They both exist and each one of them is equal to 0. Okay, so here is an example where partial derivatives exist, but the function is not continuous. And therefore, if differentiability of a function of several variables is to be a stronger property than continuity, as it is for functions of one variable, okay, its definition must require more than the existence of first partial derivatives. Okay, so mere existence of partial derivatives that doesn't suffice. Okay, for let us recall the definition again. This is sort of a motivation again. I'm sure people who are not seeing this definition, I think this definitely serves as a motivation. So a function f from R to R is a differentiable at an interior point x0 of its domain if the difference quotient as x0 at x difference quotient whenever x is not equal to x0 approaches the limit as x tends to x0. So this is the definition. Here we are talking about a function being is a function of one variable from R to R, and so the limit as x approaches x0, if this limit exists, then it is called the derivative of f at x0, and it is denoted by f prime x0. Okay, and this is what we have. This is the basic definition again. All right. Now this exercise again, I think many of you would have done this exercise. But just mentioning a function f is differentiable at x0 if and only if limit of f of x minus f of x0 minus m times x minus x0 over x minus x0 as x approaches x0 is equal to 0 for some constant m. Okay, and this is the necessary and sufficient condition for again this function is a function from R to R, a function of one variable. So a function of one variable is differentiable at x0 if and only if this condition is met. Okay, so again it's very easy to see from here. Okay, and this m here, m that is appearing here is nothing but f prime x0, is nothing but x prime x0. So we are familiar with this result, I think, no big deal. Okay, now we are going to generalize this definition for a function f from Rn to R. Okay, so this whatever we discussed on this slide was for a function from R to R. Okay, now from function from Rn to R, so we're going to generalize. So a q is taken from this definition, from this result, and one is I think the mathematicians have tried to have generalized this definition. Okay, so the definition. So note that this exercise characterizes differentiability of function of one variable in a way that suggests the proper generalization. So the generalization of a function of n variables is as follows. So here is the definition. Okay, definition 4.1. A function f defined on a domain D in Rn, maybe it's a subset of Rn, is said to be differentiable at an interior point x0. So point x0 belongs to D. It's an interior point of D. We know what is meant by a point being interior, okay, to a given set. So it's an interior point of D, hence it is interior point of Rn, so it's n dimensional. So we're talking about a function f being differentiable at this. Okay, if now look at this definition. If limit of f of x minus f of x0 minus summation mi xi minus ci divided by epsilon of x minus x0. This is the, of course, this is this is the Euclidean distance of a vector. So x of this vector x minus x0, and this quotient approaches 0 as x approaches x0. Okay, for some constants m1 and 2 mn. That is how the definition of a function f from Rn to R the function f being differentiable at an interior point is defined. Okay, I think it's having given this as a motivation, it is easy to really easy to appreciate this definition of function of several variables. Really, I mean, if I had presented this definition, the students who had not seen earlier, probably they would get lost. Okay, but having given this definition, I think this definition does make sense. Okay, first of all, if n is equal to 1, this does reduce to this. It's a simple consequence. So this does reduce to that. Okay, all right. Now the question again, you know, one can guess what should these m1, m2, mn are, this constant should be. Okay, one can make a guess. Okay, so again, so I'm just illustrating this with this example. So let function f be given by x square plus 2xy. So it's f is a function from R2 to R. And the claim that is being made is that the function f is differentiable at any point x0, y0 belonging to R2. That is the claim. And then we are going to prove this claim. Again, I think it's not a big deal. It's a simple, very, I mean, well-behaved function. Okay. So showing the differentiability, now differentiability of a function from R2 to R in this sense, that's what we want to verify. So consider f of xy minus f of x0, y0, simple algebra. This simple algebra will lead you to this. The simple algebra will lead you to this. Now if you let m1 be equal to 2 times x0, y0 and m2 be equal to 2x0, okay, then this quotient, the quotient that is there in the definition of multivariable function being differentiable, that quotient is considered. Okay, and then this simplifies to this, no big deal, and this is less than equal to this by Cauchy-Schwarz inequality. Again, I have just reproduced it here. Okay, and this implies that this goes to 0 and f is differentiable at x0, y0, and here m1, in fact, the m1 and m2 that we chose. So m1 in fact is the partial derivative of f with respect to x at x0, y0, and m2 is the partial derivative of f with respect to y evaluated at x0, y0. Okay, fine. Theorem 4.1. So if f is differentiable, so okay, I think this is again important. So we get the definition of function f from Rn to R being differentiable. Now if the function f is differentiable at this point x0, which is an interior point of the domain of f, we know what is meant by a function being differentiable at an interior point here, then the partial derivative of f with respect to x1 evaluated at x0, partial derivative of f evaluated with respect to x2 evaluated at x0, and so on, partial derivative of f with respect to xn evaluated at x0. So if this is the hypothesis, if the function f is given to be differentiable, then all these partial derivatives, first order partial derivatives with respect to x1, x2, xn, these partial derivatives, they exist. Okay, and the partial derivatives, which this ith partial derivative f of xi, x0, in fact, is equal to mi equal to 1 to n, where m1, m2, mn are the constant that are appearing in definition 4.1. Okay, so this, I think this theorem, again, I'm not going to, I think, okay, given the proof, I mean, I think maybe I can skip this proof. Okay, you can go through this. I think it's not so difficult to read. Okay, so you can follow. It's a very short proof, so you can go through it. Okay. All right. I hope, I mean, okay, I think maybe I'm going to take a short pause here in the sense that, okay, see, I told you that, you know, I'll make a evaluation scheme, I'll make it known to you this week. So I'm going to make it known to you tomorrow in tomorrow's class. Okay, without fail, I'll do that. Okay. Now the question is, okay, what I intend to do also is that I intend to convert one of the lectures as a tutorial session. Okay, so I don't want to fix a particular lecture as a tutorial lecture. So as and when the need arises, the tutorial problems, their solutions will be discussed, and at that time I will take up any questions that you may have. Okay, so I think it's difficult to take up any questions at this point of time, right? I mean, in between, I don't know how. I mean, if let me see whether there are any messages. Let's say so. Converse. I mean, if you have sent any messages, no, I don't see any messages. So I think it's going to be difficult for me to refer to these messages every now and then and try to answer your questions. Okay, so what I intend to do is I intend to reserve one lecture uh, for answering your questions, also for answering uh, for indicating the solutions uh, to problem sets. Okay, problems given in the problem sets. Okay, so again, see, I'm making these announcements. I think if you have any better suggestion, please let me know through, I forget his name now. Is it Arojit? What is, I think there's,
Yes, sir. Yes, sir. It's Arjit.
oh yeah, okay, yeah, thank you. I think, all right. So if please let me know through Arojit. Okay, if you have any suggestion, I think, so that's it. Yeah, sir, where will you share your lecture material? Okay, I'm supposed to do that. I'm supposed to upload these files on MS Teams. Okay, these notes that are being displayed to you. I'm supposed to do that. There are a few typos. I actually didn't find time during last three to 4 days to take care of those typos. So, but I shall do it by this evening. I'll upload these notes. Okay, sure, I'll do that. Yeah, any other quick comment that you would like to make? Okay, I saw Vivek saying something about the notes. So I responded to his query. I'll do that. Fine. Okay, then I think let's continue with this lecture. Okay, fine. So this proof, I would let you go through this proof. Okay, all right. So let's note the following. So a function L of the form Lx equal to m1x1 plus m2x2 plus dot 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 mnxn, where m1, m2, mn are constants, is said to be linear. Okay. So from definition 4.1, again, see, I have given this number. So see, this is, if you look at my note, this is subsection 4, and that's why I have we call this definition as definition 4.1. This is the first example in this subsection. That's why I have numbered it as example 4.11. So from the number, I think it should become clear to as to the subsection that I'm referring to. Okay. So here, now for example here, so this is theorem 4.1. Okay. So note, actually this should have been note 4.1, but doesn't matter. Okay. So the from definition 4.1, so you know from the context what I'm referring to. So f is differentiable at x0 if and only if there is a linear function L such that fx minus fx0 can be approximated so well near x0 by this. Okay. So this is a function. And from definition, f is differentiable at x0 if and only if there is a linear function L such that fx minus fx0 can be approximated so well near x0 by this Lx minus Lx0. Okay. Now this is the, so linear function has this property, so that Lx minus Lx0 is L of x minus x0. So actually what I am referring to is this part. So from this theorem, etc., it is clear that, let me go back to the definition. It is clear that this part is this is what we are referring to, linear function. Okay, and so we're trying to approximate fx minus fx0 by this linear function in the vicinity of x0, when x is in the vicinity of x0. Okay, then x is in the vicinity of x naught. That's what we are saying. So this is by this that fx minus fx naught is this plus epsilon x times the norm of this vector x minus x naught, where this limit of epsilon x approaches 0 as this vector approaches x naught. Okay. So again, I think just, when I say that this vector approaches x naught, that means coordinate wise. So the ith coordinate of this is getting closer to the ith coordinate of this and so on. Now, if it's differentiable at x naught, then it is continuous there. Okay, this is what this was the objective. I think in univariate in case of univariate function or a function of one variable, we know that the differentiability implies continuity, and then so we wanted to make sure that the function f from Rn to R, if it is differentiable at x naught, then it ought to be continuous there. Okay. So again, a short proof again. So it's worth going through this. I'm not going to skip it. Okay. So from Lx equal to m1x1, m2x2 plus dot 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 mn xn, and m1, m2, mn are not arbitrary. They have specific. Each one of them has specific meaning, and we know what the meaning is. And Schwarz's inequality, okay, will give us this, where m is given by this. And this and 2, now what is 2? This and 2, this is 2. So this is numbered as 2 and this is numbered as 3. So this and 2 imply that this is less than equal to m plus epsilon of epsilon x, the norm of x minus x naught, Euclidean norm, which with 3, again 3 is this, implies that. Okay, so as x goes to x naught, this thing goes to 0. Okay, and that implies that the function is, if the function f Rn to R differentiable, if it is differentiable, it has to be continuous at that point. Okay, fine. Now the function f given on slide number 44 is not differentiable at 0, 0. Okay, so again let's go back to this is slide number 51. Go back to slide number 44. Yeah, this function. Okay, so this function is not continuous at 0, 0 that we had observed, and the partial derivatives at 0, 0 with respect to x and y exist, and each one of them is equal to, was observed to be 0. Okay. So so it is not continuous, and hence one can use this result and to show that it is not differentiable. Okay. So the function that we had seen, that function was discontinuous at x naught, y naught at 0, 0. That was observed earlier. That was, we had noted it earlier, and it is not continuous at 0, 0. Hence, it cannot be differentiable at 0, 0. And that follows from this, essentially from this theorem. If A implies B, then not B implies not A. Right? From that it follows. So this function given on slide number 44 is not differentiable. However, the partial derivatives we noted that the partial derivatives exist at 0, 0. Okay. So the converse of theorem 4.1 is false. So even though the partial derivatives exist at a point 0, 0, doesn't mean that the function is differentiable at 0, 0. So the theorem 4.1 actually, again, let us recall this theorem. This is theorem 4.1 said that if function f is differentiable, then its partial derivative, so function f from Rn to R is differentiable at this point x naught, then the partial derivative of f with respect to xi for I going from 1 to n and evaluate x naught, those partial derivatives exist. Okay, and this example shows that the converse is not true. So even though the partial derivatives exist, the function is not differentiable, and the fact that the function is non-differentiable, it follows from this. It follows from 4 point. So these notifications keep popping up. All right. All right. All right. Okay, fine. Okay, so yeah. Yeah, so okay. Right. So there is, I think there is, I have not added this here. Okay. Uh, so let's see now. The function is, yeah, right. But there are sufficient conditions in terms of fx, fy. Okay, I mean, I'm talking a function of a function of two variables. Let's say fx, fy. So there are sufficient conditions on fx and fy, and if those conditions hold, okay, then so for example, if these partial derivatives, let me say this, if these partial derivatives, no, so when does the question is, when does the converse hold? That's the question that we are asking. So when does the converse hold? So the converse holds if the partial derivatives are continuous. Okay. So in other words, we also say that if the function is continuously differentiable, then this function is continuously differentiable, then the function becomes differentiable in the sense of definition 4.1. Okay, so I have not included it here. I'll do that. I think that part actually is missing. I'll do that. Okay, so now this is what I wanted to review. Something else I wanted to review. So let me switch over to the other set of notes. Okay. All right. So now let us talk briefly about transformations. So a function L from Rn to Rn is called a linear transformation. Again, so this is, I mean, if these two conditions hold, all right, these two conditions hold. There is more material. You see, there are about 20 slides here, but I'm going to skip all those slides because, you know, they again, these slides contain basic definitions of subspace, I mean, basis, subspace, etc. And then I think, you know, I'm sure you know those the basic definitions. So I'm going to skip all that, and I have begun with slide number 22 here, which is about transformations. Again, I'm sure all of you would be familiar with this definition. Okay. So nothing new is being told to you. I'm fully aware of that. Okay. So just bear with me. I think maybe we will start with the syllabus of optimize this course, SI 416. We will start with the new material from tomorrow. Okay. So a transformation L from Rn to Rm defined on all of Rn is linear if and only if Lx can be represented in this manner. Okay. So this is the definition of a linear transformation, and a transformation from Rn to Rm defined on all of the Rn is linear. This transformation is linear if and only if Lx is represented as this, and this can be written as A times X, okay, where A is a M cross N matrix whose first column is given by A11, A21, M1, second column is given by A12, A22, M2, and the nth column is given by A1n, A2n, and Amn. So that is so you have a matrix M cross N, and the vector X is a N cross 1 vector X1, X2, Xn. So essentially, so linear transformation, a transformation from Rn to Rm is linear if Lx can be represented as A times X, where A is M cross N and X is N cross 1, and the elements of A are all constants. Okay, they're all real numbers, let's say. So we assume them to be real numbers. Okay, so they could be complex also, but we assume them here. We are dealing with transformation from Rn to Rn. All right. Now, if L1, L2 are linear transformations from Rn to Rm with matrices A1 and A2 respectively, then AL1 plus B, again, I'm using this, okay, script L1 and script L2, but I'm going to be calling them as L1, L2. So A times L1 plus B times L2 is a linear transformation from Rn to Rm with matrix A1 plus B, A2. Okay. That is what. So, you know, with this transformation L, we associated a matrix A, and which I described to you a while ago. So, and if you're given two transformations, linear transformations, then there would exist two matrices, one A1 associated with L1 and L2 associated with L2, and then the matrix that gets associated with this new transformation AL1 plus BL2 is given by this AA1 plus BA2. If L1 again is this transformation and is transformation from Rn to Rp, and L2 is a transformation to Rp to Rm, these are linear transformation with matrices A1 and A2 respectively, then the composite function script L3, which is L2 composed in L1, defined as L3x equal to L2 of L1x. Okay, so this is L3 is a transformation from, in fact, it's a linear transformation from Rn to Rm, and the corresponding matrix is nothing but the product of the matrices A2 and A1. Okay, so the product of these two matrices A2 and A1. Okay, this being a linear transformation, there would correspond a matrix, and that matrix is given by A2 times A1. All right. If we regard the vector x as an n cross 1 matrix, then the linear transformation in 1 can be written as this. So this, I think, linear transformation 1, it is this is what we are referring to. Actually, I should write 1 here. Okay, and it is given by this. So that is again, all right, exercise, all this is. So this is again, I think it's not worth going through all this. This is simple, whatever I mentioned or whatever I stated through in this result or in this theorem, the same thing is very illustrated using these examples, not worth going to. Okay, fine. Again, you know, you have, you know, the composition of two linear transformations, etc. So this is the routine stuff. And again, point is that the matrix corresponding to L3 is obtained by A2 times A1, and it's given by this. So this is A2 times A1. This is not. This is wrong. This is wrong. There's again this typo here. This must be A2 times A1 because A2 is 3 cross. This is let's say 3 cross 2. Okay, and this is 2 cross 2. So this, I'll correct this. Okay, so again, eigenvalues, eigenvectors, etc. I'm going to skip that one. Okay, there's maybe let me see just okay, this. So again, just in case some of, I mean, maybe some students have forgotten, if suppose the characteristic equation has n distinct roots, then there exists n linearly independent vectors. This is an important result. So I think I just want to highlight this. Okay, this is what it is. All right, I'm going to skip this. So all eigenvalues of a symmetric matrix is a standard result. Any real symmetric n cross n matrix has a set of n eigenvectors that are mutually orthogonal, standard results. Okay. Now orthogonal projection. Now recall that in the definition 2. So definition 2, if you go back to definition 1.2, it's not definition 2. If you go back to definition 1.2, actually I did not display this. This gives you the definition of a subspace. So recall that a definition 1.2, subspace of Rn is a subset that is closed under the operations of vector addition and scalar multiplication. Furthermore, the dimension of a subspace nu is equal to the maximum number of linearly independent vectors in U. Okay. So if nu is a subspace of Rn, then the orthogonal complement of nu is defined as this. So collect all those vectors whose inner product with every vector in the subspace nu is equal to 0. And this collection, okay, this collection This is the set of vectors that are orthogonal. Okay, so this itself, this is orthogonal subspace, and this is a subspace, and these two span Rn in the sense that every vector x in Rn can be represented uniquely as x equal to x1 plus x2, where vector x1 belongs to nu and x2 belongs to its orthogonal counterpart. The representation is called orthogonal decomposition of the vector x with respect to nu. Okay, and x1, x2 are called orthogonal projections of x onto the subspace nu and nu t respectively. So here Rn can be written as this, a direct sum of nu plus nu t. Okay. Now linear transformation P, we just saw what is meant by linear transformation. So linear transformation P is an orthogonal projector of onto nu if for all x belonging to Rn, Px belongs to nu and x minus Px, it happens to be in this nu, this subspace nu t. Okay. Now let A be this AB belong to R raised to m cross n. So essentially what we are saying is, because you know this is a m cross n matrix, this is a m cross n matrix, and every element of this A is a real number. Let the range or image of A be denoted by this. Okay. Range or image of A be denoted by this. And the null space or kernel of A is denoted by this. This is null space of this. And again, it's a standard result that this range and the null space, these are subspaces. So one can verify the definition of a subspace here. Okay. So let A be a given matrix. Then this is given by this, and you have this given by this exercise again. Okay. And matrix P is orthogonal projector onto the subspace nu if and only if P square is equal to P transpose. Okay. And exercise. So again, I'm going to skip the definition of quadratic forms. We know what is meant by a quadratic form. Okay. And we know what is meant by or when we know when we say that a quadratic form is positive definite or non-negative definite or positive semi-definite. All these definitions are quite standard definitions. Okay. All right, I think. So all this basic stuff can be found here. Okay. So maybe I think I'm running out of time. Maybe I think let me not start with this. I think we maybe I can define this as and when this is required in our course. So I'm going to skip this. I'm not going to discuss this at this point of time, or maybe in tomorrow's lecture. Tomorrow's lecture I shall begin with the first topic in optimization course. Okay. So let us stop here. And we shall meet tomorrow at 11:35. Okay, any quick comment that you would like to make?
So, I have a doubt. Theorem 4.1 converse is true only if the partial derivatives are continuous. Is it the case that the only first order partial derivatives to be continuous, or all the partial derivatives will be continuous?
1 second. 4.1 theorem. 1 second. I'm going to go back to that.
So where we have the partial derivatives. of the differentiability from the differentiability.
For theorem 4.1.
Yes, sir.
See the
So for the converse to be true.
for the converse to be true, you're asking.
Yeah. So only the first order partial derivative should be continuous, right?
Yeah, they are required to be continuous. Yes.
Okay, sir. Thank you, sir.
Okay. Fine. All right then. I think I'm going to stop this recording.